Hi guys, I will be solving your questions in impulse momentum test. So first question, you're basically on the moon and then acceleration is 1/6 of what it's on Earth. You apply some force for a time of t. So once you think about force and time together, then we need to directly think about change in momentum. And change in momentum is basically mass times change in velocity. So well, it doesn't state that it was actually at rest initially, but what's happening is after you apply the force over a time of t, your velocity becomes v. All right, so your v final is going to be v. However, so one thing that we need to consider in this case, the direction of force and the direction of velocity. So once I actually erase this, whoops. So once that you erase the force, you basically have the club and the object. Object is going to have some velocity with an angle, but to be able to give that velocity to the object, then the force must be applied in the same direction as velocity, because acceleration and velocities are basically two vectors, and then whatever the direction of acceleration or the force, then object needs to accelerate in that direction. So velocity will be in the direction of the force. So basically this force and v are applied parallel, so the angle in between the ground and the object or the club is not going to be important in that case. So then it's just going to be m. It doesn't state that it starts from rest, but we can just assume. So v minus 0, because final velocity is just v, initial velocity is 0, f times t, and they're basically asking for average force, so it's mv divided by t. So you don't need to worry about the angle or gravity at all. All right, next question. You are basically holding the ball. Yeah, my drawing is awesome, I know. So you basically hold the ball initially at this location, and then you basically move your hand 0.9 meters throughout the motion, and then you basically reach, not you, but the ball is reaching to a velocity of 30 meters per second, and then they are still asking for the force. And so in this case, we know initial velocity, we know final velocity, and we also know the mass of the ball. It is 0.2 kg. So you know initial, final velocities, and mass. So that means you know change in momentum. And then they're asking a force. So then you should directly think about F delta T equals delta P, or change in momentum. So F is the question mark, but I also don't know the time for me to actually go from one location to other. However, they give me additional information. They give me the distance. I know the initial and final velocities, and I know the displacement. Then you are going to think about kinematics equations. So delta x equals t over 2 v final minus, not minus, plus v initial. So in that case, since this is 0.9, t over 2, and this is 30, then your t is basically 1.8 divided by 30. So I'll just use this as 1.8 divided by 30. And change in momentum. So we are talking about the ball. So mass of the ball is just 0.2. And change in velocity in that case, 30 minus 0, which is 30. Then my force in that case is going to be 30 times 30 times 0.2 divided by 1.8. So dividing those two, you will get 9, and then you're going to get 9 divided by 30, 10 and 3, 3 and 30, 10. So it's just going to give you 100 newtons of force. All right. So again, the idea is knowing initial and final velocity. You think about impulse momentum relationship directly. And after that, you also think that distance is given, then you can find the time, and then you basically move on. Alright, so you have an object drop from certain height. Right before it hits the ground, its initial velocity is just vi. Right after it actually bounces off, its velocity is v final. And the question is, what is the magnitude of the impulse? So impulse is, yes, ft delta t. F delta t is change in momentum, or this is the definition of impulse anyway, so you can just directly use delta p. So what is delta p? M delta v, and then it's just going to be m v final minus v initial. So in that case, this is the equation. But considering the signs, your v final and v initial, they are opposite in direction anyway. So v final is already a positive number because it's going up, but v initial is going actually downwards. So your change in momentum in that case is going to be v final minus v initial, because vi is just a vector. So we don't really know what the number is, but this negative sign is going to be due to the direction of it, and this negative sign is because of the function delta. Then your final answer will be m v final plus v initial. So your answer is C. So momentum is a vector quantity. You guys need to be careful with the direction. So change in momentum, so ft graph is given, change in momentum is directly the area underneath. It's a triangle. F is the height, t is the base, divided by 2. That's your answer. Alright, so another question was the impulse. Impulse is again m delta v. So we don't have force and time, so then you just directly go with the change in momentum. But again, remember, velocity is a vector quantity. So this is going to be your final velocity, and this is going to be your initial velocity. Then what is delta v? It is v final minus v initial. So v final is basically going in this direction, and v initial is going in that direction, but you basically need to change the direction of it, and then it is going to be minus v initial. Then what is my basically direction? So my change in momentum is going to be basically this vector, so delta v. So how are we going to basically find that delta v? So these are basically the same numbers, so I can just use as v and v, and delta v function is going to be alright, so I need to think about the geometry of this guy. So alright, so we need to divide it into 2. So this is my angle theta, and then I know that this distance and this distance is the same. My hypotenuse is v, my angle is theta, so I need to find this distance. And how do I find that distance? It's basically adjacent side of the angle theta. Then it is going to be basically v cosine theta, but you basically have 2 of those vectors, so your delta v is going to be 2v cosine theta. But this is change in velocity, but they're asking for the impulse, so I also need to include the mass. So my impulse is going to be 2mv cosine theta. So this is going to be E. Alright, so you have one object going with v and the other object is at rest. Both have the same mass and the collision is elastic. Alright, so the collision is elastic. So that means total energy and total mass is conserved. Alright, another thing that we need to consider or know about elastic collisions, if they have the same mass, they just switch their velocity. So what does that mean? After the collision, well, the color is not going to be the right, but this guy is just going to be stopping, and then the other guy is just going to be moving with v. And if red one had actually like some velocity and the blue one had different velocity, after the collision they just switch their velocities. That's how it actually applies if it's an elastic collision and if they have the same mass. Alright, and since it's an elastic collision, then you can also just think about total momentum and total kinetic energy is conserved, and the answer is A, but we're going to need that switching velocity information in the following, one of the questions I believe, but that's what you guys need to know about elastic collisions. They switch their velocities if they have the same mass, and momentum and kinetic energy is conserved. Alright, so this is very similar to the first question, except this is not with numbers, this is just with the variables. So you initially start from rest, you apply some force over a period of time, and then you apply that force for some distance delta x, and what is the magnitude of the resultant change in momentum? So, well, it's a lot simpler than that actually. I believe that was a two-part question. So change in momentum is just technically just f delta t. So delta t is given, f is also given, so it's just f delta t. Alright, so next question. One object is at rest, but it's twice mass of the first one, and after the collision, first object bounces back with v over 3, and the question is what is the velocity of the second object? Well, you just apply the conservation of momentum. So momentum of the first object plus momentum of the second object is equal to momentum of the first object plus momentum of the second object. This is the initial case, this is the final case. So initially, momentum of the first object, which is A, is just mv, and momentum of the second object, since it's at rest, is just 0. And after the collision, momentum of the first object, which is just m, and velocity v over 3, so mv over 3 plus momentum of the second object. So we don't know the direction of velocity, so it's just going to stay as v, but the mass of this guy is just 2m times unknown, which is x. So if you would like to just rearrange the question, so you have mv over 3 in this side, so you just move it to the other side. So mv minus mv over 3, and it is equal to 2mx. And if you do the math, 2mv over 3 is equal to 2mx. Then 2m's will cancel out, so your x will be v over 3. Since it's positive, then it's just going in the right direction. Alright, so the next question, not the second. Head-on collision, and then it's perfectly elastic. Like I said, there's no difference in between elastic and perfectly elastic, so kinetic energy and momentum is conserved. So before the collision, x has velocity of 2, the other has 4. After the collision, the ball x has a velocity of. So like I said, since it's an elastic collision and they have the same mass, then they will just switch their velocity. So x is just going to go with 4 meters per second to the left, and y is just going to go to the right with 2 meters per second. So 4 meters per second to the left. Alright, so you have a toy spacecraft is launched directly upwards. When the toy reaches to its highest point, that's going to be an important information actually, a spring is released and a toy splits into two parts of masses of 0.1 and 0.9. And after the separation, 0.1 goes to the right with some speed. And which of the question or which of the statements below is correct for the other part? So since it's a conservation of momentum, and at the maximum height, what do we know? At the maximum height, it's just going to reach to zero velocity. All right, so that means it is actually at rest. So what does that mean? Initial momentum of the system is just 0 meters per second. Afterwards, what's happening? 0.1 is moving to the right with some speed, but I would like to call it 9v, because due to the conservation of momentum, total momentum must be 0, right? So if the piece that is moving to the right has 0.1 mass, then the other piece that has 0.9 mass should actually have 1/9 of the speed, so that total velocity, total momentum is still 0. And how is it possible? Because momentum is a vector quantity, so vector to the right should be equal to the vector to the left. So when you add those two momentums together, your total final momentum is still 0. So basically, this large piece must go to the left with some speed that is 1/9 of what it was for the other piece. So, and let's see what are the statements. It could move north immediately after the spring is released. So due to the conservation of momentum, so the only momentum is to the right. So you have to have a momentum that can cancel that and nothing extra. So since the only momentum to the right, then you can only have momentum to the left, not north, not south. So this is not going to be a correct statement. And after that, it takes longer to reach the ground when it does 0.01 kilogram apart. Well, at this point, we are saying that they are going to have velocities that is going right and left. But for them to fall to ground, we are basically seeing that they are basically at the same elevation. And for their vertical movement, their horizontal velocities are not important. So it's just going to take the same time for both of them to hit the ground, actually. So for the third one, it strikes the ground, and it refers to the large piece, closer to the launch point than thus the 0.01 kilogram. So right now we are basically talking about the displacement on the horizontal axis. And this guy is going with 9v, and this guy is basically going with v. So that is going to just fall right here, but this guy is just going to fall somewhere over here. So the third statement is correct. So your answer is B. All right, so you have a child, this guy. It's running with 3 meters per second, and he is 25 kg. That's like 45 pounds. So running to the speed of and it is basically jumping on a stationary sled. So initially this guy is 0, and basically after, and the mass of this guy is 5 kg, and then what will be the speed after he actually jumps on the sled? Well, that's another common conservation of momentum type of questions. So P1 plus P2 equals P1 plus P2. And this is the initial case, and this is the final case. So momentum of the first. So it doesn't matter which one you choose as the first object, but it's of course like common to choose a person as the first object. So what is the momentum of this guy? Its mass, which is 25. What is the velocity of this guy? 3. Plus momentum of the second object. So it's 5 times 0. 5 is the mass, 0 is the velocity. And then since they are basically moving together, then it's going to be perfectly inelastic. It doesn't really matter what the name is, but you are basically going to have 25 and 5 kilogram of mass with some velocity that we don't know. And after this, you just do the math. 25 plus, 25 times 3 is 75. It's equal to 30 V final. And once you divide both sides by 30, then your V final is 15, 2, 7. What am I doing? 5, 2.5. Did I do it right? Yep. So the final velocity will be 2.5. So basically you are thinking about conservation of momentum, and then you write individual momentums respectively, and then you solve it for the unknown. All right. Most of the conservation of momentum questions are going to be like one object at rest, the other is just hitting to the other one, and you just need to be careful if it's perfectly elastic, perfectly inelastic, because if it's perfectly inelastic, then they just hit and stick together. All right, so let's see. We have V0, M, and then 2M initially at rest, and it is elastic. So that means total kinetic energy is also conserved. Which of the following correct shows the motion of the blocks after the collision? Well, conservation of momentum and conservation of kinetic energy in this case. So total momentum of the system must be V0 times M. This is the total momentum, because initially 2M doesn't have any momentum. And total, so we can just directly start doing that. And so this guy is V0 over 3. So this is 2. Another V0 of 3. Is it? All right, I'm being honest. There is another equation that is basically helping us to solve those type of questions, but I forgot that at this moment, so I will just try to solve that without considering that. All right, so total kinetic energy is going to be what? 1/2 mv0 squared. So this is the total momentum that you need to have. This is the total kinetic energy that you need to have. You need to conserve both of them. So and you should also recognize, well, not recognize, but we weren't able to, I'm not sure if we did the experiments in class, but once you do the elastic collisions, then they're going to bounce off. It doesn't matter what the masses are. So you can't expect them to go at the same direction, or you can't just expect them to be at rest. And momentum is a vector quantity, so we can just calculate the momentum of this guy. So it is negative V0 over 3m plus 2 V0 over 3 times 2m. So that makes 4m V0 over 3 minus V0m over 3. And once you add them together, you find that total momentum is m0, mv0, and that's what you had at the beginning. So by basically selections, that's what you have. All right, I'm going to actually, well, this is the answer. You can just basically go like that, but besides that, there was another equation that you can just combine conservation of kinetic energy and conservation of momentum equation. And I remember I gave you that equation, so you can just visit that equation and then solve that mathematically. But right now I just did it conceptually. All right, next question. You basically have x and y. X is 3m, y is m. You drop them from the same height. So right before they hit the ground, they have some kinetic and potential energies. So what are the momentum and kinetic energy of x just before it reaches the ground? So they give you this as ky and py. And then what will be the momentum of x and what will be the kinetic energy of x in terms of the momentum of and kinetic energy of y. So one thing that we need to consider or recognize is the only difference is in the mass. And the other thing that we need to recognize, they are basically dropped from same height. So that means when they are in the ground, mass is not important. They are going to have the same velocity. And kinetic energy is basically calculated with 1/2 mv squared, and momentum is calculated as 1/2, nope, not 1/2. So it's just mv. So both of them, x and y, have the same velocity. So the velocity is not going to be important. So whatever the difference of the mass, then that will be basically the difference of kinetic energy and momentum. And since x is 3 times more than the mass of y, then kinetic energy is also going to be 3 times of what it's of the object y, and momentum is also going to be the 3 times of object y. So in that case, your answer is going to be B. All right, two blocks of M and 2M are frictionless horizontal surface as shown below and are held in place with compressed spring of negligible mass between them. So if the blocks are then released and block of 2M leaves with a velocity v and the velocity of the center of mass, that's a center of mass question. Well, center of mass, basically velocity of center of mass is going to be total momentum divided by total mass. All right, so and it doesn't really matter if it's below, if it's before or after. So you don't really care about if you're looking at the initial or final condition. All right, so for initial conditions, since they both were at rest, after this release, your center of mass has to stay wherever it is. So that means this guy is going to go to the left with 2v, and this guy is going to go to the right with v, but the center of mass is just going to stay wherever it is because initially they were at rest. So velocity of the center of mass is just going to be wherever it is. But if they were asking for what's the velocity of m, you could just say 2v because the other is just twice of the mass. So to be able to compensate that, it's just need to have double of the speed. All right, and the last question, you basically have 1,500 kilogram object going with 4 meters per second to the right, and another object with 3,000 kilogram going to the left with 3 meters per second. They collide, stick together. What's the velocity afterwards? So this is again conservation of momentum. So total momentum, initial and final, must be the same. Initial P1, P2 equals final P1, P2. So initial momentum of this guy is basically 1,500 times 4 plus 3,000. All right, this is the key part, -3, because this object is not going right, it's going left, and momentum is a vector quantity, so you need to be careful with the direction and sign. And at the end, they stick together, so we are talking about 4,500 kilogram system, and we don't know the speed of that. So initially, we basically have 6,000 minus 9,000 equals 4,500 V final. So basically negative 300,000 is equal to 4,500 V final. Divide both sides by 4,500. And then you find your V final as, what do you find? Divide by 3? No. What do we do? So it's 3 divided by 4.5. And this is 6 over 9. And this is 2 over 3, which is 0.67. Or 2 over 3. Alright, so basically this is the solution for the last question. Well, the last part is just this algebra. But that's how we solve impulse momentum questions. So from the given quantities, you just think about what you know, what's the unknown, and just apply conservation of momentum or impulse momentum relationship in the questions. Alright, thank you for watching. See you in the next video.